just to give you a brief overview of what we're going to be going over today, we'll be covering all the basic concepts that you need to work effectively in iolite. So although some of it is establishing some terminology and getting down some basics like how to make selections, these are really fundamental things for using iolite, and they're used for any sort of experiment that you might run. So for example, today we'll be looking at trace elements, but if you were to be doing, say, uranium lead, you'd follow pretty much the exact same process. You just run a different DRS. And if you're doing imaging, there'd just be a couple of steps at the end that you do, but otherwise it's the same. So this is really the fundamentals that you need to be able to do anything in iolite, really. We'll give you a quick tour of the user interface. So it will be just brief. There's a lot of features in iolite 4. We won't be able to cover most of them because quite a few of them are advanced. For example, if you're doing things like split streaming, then that's all entirely possible, but we won't be covering that today. We'll be looking at importing data, so actually getting your data into iolite, which is the important part. Then we'll be looking at how you can actually navigate around those data and inspect them, and how to create selections. So there's lots of ways of creating selections in iolite, but we'll be covering the most fundamental ways. And then we'll be looking at calculating results. So using a data reduction scheme. And this is how you go from your input data to your final results. And of course, it's really important that you actually view and interrogate your data, make sure that you've got the best results that you can, and you're not including any rubbish data. And so we'll be looking at viewing and running some quality assurance, quality control, and also exporting your data. So we'll start off with some terminology and some of the basics. And the most basic concept in iolite is the idea of a selection. So a selection is just a defined time period. And iolite uses that defined time period to report a mean or a median and an uncertainty associated with that time period. We collect selections into groups so that we know, so that iolite knows what's happening at a particular time. So for example, when you select your NIST 612, you put that into a group called the NIST 612 selection group, and then iolite knows when NIST 612 was measured. The selections don't have to be exclusive. So for example, you could have a secondary reference material, say BCR2G in the example we're going to look at today. And it could be selected as a secondary reference material, but you can also have it in another selection as well. And you can have it in as many selection groups as well. The idea of this is that you can group your samples according to different properties, and they don't have to be exclusive. And as I mentioned, selections form the basis for our results. So for each selection, you'll get a mean and an uncertainty, but they are also how we define splines in iolite as well. And even though we might define a selection looking at one channel, it actually has a value for every channel. And selection groups, just so you know, can be one of 3 types. They can either be baseline selection groups, they can be reference material selection groups, or they can be samples or unknowns, we sometimes call them as well. So just a little bit on the statistical side of things, all the data in iolite are processed on a time point by time point basis. So this means that we don't do any averaging until the very end. This has a statistical implication that we're looking at things from the mean of the ratios, if we're taking ratios, versus ratio of the means. By keeping everything in time resolved mode until the very end, it means we can do a whole bunch of things like downhole corrections, more detailed interpolation, splining, those sorts of things. So let's talk now about channels. So we have a lot of channels in iolite that we look at. And the most basic definition of a channel is that it's just an array of data values. So if you think of like a column in a spreadsheet. And that would be your results. So that would be a channel. So for example, when you import your data, you might have a magnesium 25 or a strontium 88 channel. We also calculate channels as iolite steps through the process. So it will have the raw data, but then it will create intermediate channels and output channels. So for each step in the process, it will create a new channel, and then you can view those channels later on, so you can see every step of the process. So this is just an example where we can see our channel data. So this is one channel in blue, another channel in orange, and you can just see the laser switching on, and it's firing, and then it's switching off again. So selections, as I mentioned before, they're just a defined time period, and it tells iolite how a certain time period fits into an experiment. So here's an example where we've selected some NIST 612 runs. So these were a couple of standard runs before, some samples, and then some more at the end. So these are 610, apologies. And these are put into selection groups. So these NIST 610 selections are put into a NIST 610 selection group. So I've mentioned splines once or twice, and these are how iolite works out a value for any time point in our experiment. So for example, there's a baseline spline for every channel, and that is an interpolation or sometimes an extrapolation of that channel at any point during our experiment. So it's a little hard to see here, but there's a green line down the bottom of this plot here, and that would be our baseline spline. So for this channel. So when we do the baseline subtraction, this is the value that we're actually subtracting for every data point. So as I mentioned, we calculate everything on data point by data point basis in iolite. So when we do baseline subtraction, we don't just subtract a mean value from everything, we actually subtract the value of this line from every data point. And iolite gives you a lot of different options for splines. So it allows you to use everything from a mean value for the session through to a linear fit, linear interpolation. You can have step functions, and you can go all the way up to smooth cubic splines. In this example here, we have a smooth cubic spline, and you can see that it's gently decreasing as it goes along and then flattens out. This is looking at a sulfur 34 experiment. And I guess the idea of this is that you can choose the most appropriate spline for the job in iolite. And just to finish up the terminology, when we mention a session, we mean a self-contained analytical session. So normally from when you switch the mass spectrometer on until you switch the mass spectrometer off, everything that's done within that time we would call a session. So it can be multiple files, it could be as many samples as you like, but after you turn the mass spectrometer off, that would be the end of that session. And when you import your data into iolite and you make selections and you calculate channels, these are all stored in a .io4 file. And that's what we would call a session file. And this is actually, even though it's got this .io4 file extension, it's actually this HDF5 file format. It's an open standard file format. It was originally developed, I think, by the atmospheric scientists. And it is, because it's an open and standard data format, you can actually open it with other programs and look at your results in other programs. So now that we've got the terminology out of the way, we'll look at the basic data reduction process. So the basic steps that you would take in any experiment would be that you import some data, you create some selections for your baselines, your reference materials, and your samples, and then you select a DRS, a data reduction scheme, and you run it. And then you would view your results, and then you'd export your data. But even though that's the way we'll be looking at it today, for simplicity's sake, I want to point out that you can do these in many different orders. So for example, I mean, you always have to import some data first, but you might create some selections, run the DRS, go back, create more selections. You might view some results, go back and adjust your selections, and then eventually export data, etc. So even though I'm presenting it in a kind of static way, there are many ways to do it. So we'll have a quick look at the iolite user interface now. So I'm just going to share iolite with you now. Okay, so when you first start iolite, you should see this window here. And on the left-hand side, it'll have some recent sessions that you've run. These are files that you've saved within iolite. You can open any of these by double-clicking them, or you can click other to open an existing session file that you've saved somewhere else that's not in the list. But if you want to start a new session, you can click on the new button down here. On the right-hand side, we have templates, processing templates. We won't cover those today, but they are a way of, if you're doing the same thing over and over again, then you can set up a processing template and automate much of the work that you would normally do by hand. But for now, we'll click on New. So feel free to follow along with me for this webinar. I will say though that there will be times when I might go a little bit fast for some of the beginners. If that's the case, feel free to just let it go past you. And we're recording it, and when we put the video up, you can always catch up on what we did using the video. So don't feel stressed about trying to keep up if it's going a little bit too quickly. Hopefully we won't go too fast. So when you click on the new session, you'll see the main iolite window, which looks like this. Up the top here, we have the menu bar, and in the session menu, you'll see the options for loading and saving sessions. The tools menu here is really helpful. There's a bunch of tools in here that you'll probably find quite useful. In particular, for people who are moving from version 3 to version 4, this import iolite 3 reference material file tool allows you to bring in reference materials that you've made in iolite 3 into iolite 4. There's also Visual Age here, and the data syncer for split stream experiments, and there's the calculator for calculating your own channels. In the edit menu, there is this undo and redo options. A lot of actions are undoable. So for example, deleting selections, if you accidentally delete a selection, you might be able to undo it. Not everything is undoable. But if you have done something and you want to redo it or undo it, just check the edit menu, see if you can do it. There is this window menu, and this allows you to view the different parts of iolite. But in particular, one of the best things in here is this notes panel here. So if you click on the notes, it'll pop open this little panel by default on the left-hand side. And in here, you can write notes. So these are my notes. And you can style this up. Sorry. It's not letting me move. There we go. So you can style these up. You can put in different headings and subheadings. And as we'll see later on, you can actually drag pictures and stuff, screenshots and stuff into this, and it's all saved with your experiment. So if you're making decisions about which samples to keep and which samples to exclude, or certain parts of selections to be excluded, you can keep some notes in there. For the time being, we'll just close that. Then in the help window, we have the manual, which you can pop open the iolite manual. It's pretty much exactly the same as the online documentation. I actually prefer using the online documentation, but the manual's there as well. And you can also check for updates here as well. Okay, so now I'm just switching back and forward between PowerPoint and iolite to make sure I don't miss anything. I think I've got everything. Okay, so the other important part of these is the preferences. So on a Mac, it's here. On Windows, it's in the session file. But if you open that up, you'll see that this is where you can set a lot of iolite's preferences. So the most important ones of these are the import section if you're using using an Agilent instrument or an X series instrument. But there's also this paths section here where you can tell iolite where certain things are stored on your computer, and we'll come back to this reference materials one later on. You can also change how stats are calculated. So for example, anytime iolite reports the result for a selection that is not a baseline selection, it uses this. So it'll report the mean with 3 SD outlier rejection. And you can change that here. You can do it with no outlier rejection. You can do it with 2 SD outlier rejection. You can use the median versus and add and so on. The license section here is where you can set up your license details. If you're moving from one computer to another, you can click this deactivate license on this computer. That will then free up an installation on another computer, so you can install it on another computer. And there's some other more advanced settings here. But we'll come back to this in just a little bit. So now looking at the iolite window in more general, we have along the left-hand side, we have these series of views. We call these views down here. So we have the data browser view, the time series view, the DRS view, and so on. And generally these work from the top going down to the bottom. So generally you'll start in the data browser view, you look at your data that you've imported and your results in time series view. And then as you make your way through your experiment, eventually you'll get to export, or you might be doing imaging and so forth. But generally it moves from the top to the bottom. In each of these views, there might be a series of tabs along the top. So for example, in the data browser view, we have the files browser. So this is where you import files. So you can click on this import file button and that will import files. You can import laser log files here. You can also import whole folders here. And then once you've loaded the files, you'll be able to see the samples that are contained within them in the samples browser. So this is the samples browser, and it will show all the samples that were contained within your mass spec files here, and all the samples that were contained within your laser log files down here. And we'll come back to that once we've actually loaded some data. Here's the channels browser. So we haven't loaded any channels at the moment, but you can see information about your channels here. And this is the selections browser where you can move, delete, update the information, metadata about selections here. And this is the reference materials browser. So by default, you should all see some standards here, the ones that come with iolite by default. If you, on the left-hand side here, there's a list and they're grouped according to their matrix. And if you open one of those matrix types and click on a standard, you should be able to see some metadata about that standard. So for example, this one, we've made a note that the values were correct in 2018, but if you were to update those, you could update that value then. And if you click on this data tab, you can see the actual values for your reference materials. So it can make it a bit easier than in iolite 3, where you had to step through a few things. This is now where you can view all your results quite easily. So we've gone through each of those. So this is something that you don't need to do now, but basically there's a couple of things to note about the reference material folder. So there is a reference material folder that contains each of your each of your reference materials as its own text file. So NIST 612 will have its own text file, NIST 610 will have its own text file, and so on and so forth. And in each file, it has the metadata and the values for that standard. By default, these files are kept in the reference materials folder, which is on Windows in C program files x86, iolite software, and then iolite 4. if you're part of the beta program, this folder might be called iolite 4 beta. On Mac, they're actually within an iolite 4 app package in the applications folder. So it'll look something like this. And one of the key things about these default locations is that when iolite is updated, it automatically overwrites everything in those locations. It does this purposely because it's to ensure that we have a complete update, but it does mean that it will overwrite any changes you've made to your standards. So if you've put in custom files in there, they'll be overwritten. If you've changed your values, they will be overwritten there. It also means that you will need admin access to change any values in these, in particular on Windows, you'll need admin access to be able to change any of your reference material values. The way to get around that is that you can just move where your reference material folder is. So you can just copy it out of these default locations and put it somewhere else on your disk, and somewhere where you have you definitely have read-write access, and then you don't have to worry about it being overwritten during updates, and you also don't need to worry about having admin access while you're changing values. So for example, on Windows, there'll be, if you look in program files x86 and the iolite software folder and the iolite 4 folder, there will be a series of folders. In particular, we want this reference materials folder. And I would actually go to somewhere like your documents folder and just create a new folder. You could call it something like my iolite folder. And then once you've created that folder, you can just copy the reference materials folder into there. On Mac, it's a little more tricky in that it's contained within the iolite 4 app bundle. So in your applications folder, you can see all of your different applications, but each one of those applications is actually a bundle of folders. And to see them, you actually have to right click on the application, and then there'll be this option that says show package contents. If you click on that, it'll actually show you the contents of the app package. And so there'll be these folders here that you can see. And this is the folder that we're interested in particular. You can copy that folder out and put it somewhere else on your disk. You don't have to do this for the webinar. I'm just pointing it out so that in the future, if you have troubles with those issues that I mentioned of things being overwritten, you can do that. But when you do move it, you will have to let iolite know where you have put it. So in the preferences, you'd have to go to the paths section, and in this reference materials path, if you click on the little folder icon, it will ask you to select where you've put your new folder. And so you can just navigate to where you put the folder, click OK, and this path will show where it is. And then when you click save and go to your reference material browser, it will show, should have all your reference materials then. Okay, so now we get to the more interactive side of things. So we'll look at importing some data. So hopefully everyone has downloaded the example. Oh, sorry, I've got a few people asking how to add a new reference material. So I'll just quickly show that. You can either just copy an existing one. So Zoom is covering up the buttons for me here. Let me just move that. So you can either just click on a reference material and say copy, and that will create a copy for you. And you can use that as a template to update the values. They can be a little bit slow. You can, so I'll delete that one. You can also click up here, this plus button, and it will create a blank file for you that you can fill in. Or you can also click on this plus button to see this from GRM preferred values. And iolite will, if you have internet connectivity, it will connect to the GRM database and will pull down the values for you. There is a bug with that in the current version, or there was a bug, it might be fixed in the currently released version, where if there were if there were blank values, it might cause trouble, but we fixed that now. So you can actually import values there. Okay, so now we'll look at importing data. So one thing to note about importing data is we have trouble with the timestamps that are recorded in the data files, especially from Agilent and X-series files. Pretty much every other mass spectrometer format is okay. But in these files, sometimes it just will have something that looks like 5/6/2017. And we don't know if that is the 6th of May or the 5th of June. Sometimes it's also in the year, then the month, then the day, or sometimes it's the year, then the month in words, and then the day. And all of these variations, because computers are quite dumb, they can't work it out. So we have to tell it exactly what the file format is. Just one thing to note for people coming from version 3 to version 4. In version 3, you had to tell iolite what the instrument was that you were importing from. In iolite 4, it'll automatically determine which instrument it is. One thing about the Agilent data import is that you can actually now import the entire batch folder. The advantages of doing that is that there is a file in there that has a set format. So we don't have any timestamp issues. You don't have to set the time format. It'll just read it and work for you. And it automatically imports all samples within the batch. And it also imports the metadata. So for example, the dwell times will come in automatically, and that can be really handy if you're calculating more advanced excuse me, limits of detection. Joe's just pointed out via the chat that just for those who are importing georem values, it can be a little bit of a slow process. So let's actually import some data. So there is this Gabbros_data.csv file. This is an Agilent file, and it has a timestamp in this format here: day, month, year, hours, minutes, and seconds. We don't actually have the batch folder for this one. We normally use the batch folder, but because this is an older file, we don't actually have the batch file. This is a spot analysis experiment. So we're drilling a pit, then move to another sample, drill a pit, and we measured during the experiment some NIF612 runs, some BCR2G runs, and some BHBO2G samples. And these second two are basalt standard glasses, and we will use those to check our data. During the experiment, we're actually looking at some plagioclase, some olivine, some clinopyroxene, and some opaque phases. For those of you who are not geologists, these are just different mineral types. They're all silicates except for the opaques, so they have very little silicon in them. And we've shortened the names from plagioclase to plage, olivine to olive, and clinopyroxene to CPX, and opaque to opaque. Okay, so let's actually import those data. So to import our data, we go to the Files browser, which is in the Data browser view. So I've clicked on this here. If I needed to change the timestamp, I could just click and hold this import button, and it'll bring it up here, and you can change the timestamp here. We should be using this day, month, year, hour, minute, second option. If you hover over these, it'll give you the codes for what the different things are. And with that, we can just click Save and Import. Okay, so we're in the Data browser view and the Files browser, and we're going to click on the Import File button. And we're going to load this file from the example data, and it's the Gabbro_data.csv file. When you click on that, there'll be a little progress indicator down here to tell you how it's gone. If there was an error, it would tell us down here that there was an error. And it would probably tell us to look at the messages view. So down the bottom here, we have this messages view. If we click on this here, it tells you anything, anytime something about your session has changed, it will leave a message here. It'll log a message here. So it's told us that it's loaded 24,000 data points from this file here. And as we go through our session, it will keep adding messages here so that we know anytime we've changed our session. The only time it doesn't log something here is when you make manual selections, but otherwise there'll be a value here. And you can export this with your experiment so you can keep a clear track of what's happened during your experiment. So now that we have a file loaded, you can see that it has, we now have an entry in our data files, but we also can now go to our samples browser, and we can see that because this is an adjuvant file, there is just a single sample here. Adjuvant files only have one sample in them, but if we'd loaded, say, an ICAP file or one of the other, or an X series, or one of the other file types, then we might have multiple samples here. Similarly, if we'd loaded a bunch of files here, many files, then we would be able to see each of these. So if you set up your experiment so that you have a file for every scan line or for every sample, then you'd actually be able to see each of those here. Just have to move this down because it keeps being covered by Zoom. So now we've loaded some data, we can actually go to the channels browser. So if you go to the channels browser, you can see that we have input, intermediate, and output channels. At the moment, we haven't calculated any intermediate or output channels, so we only have input channels. If you pop those open and you click on one of the channels, it'll give you some metadata, some summary information about that channel. If you click on the time series tab, it will show it as a basic time series, so you can check that to make sure it looks okay. And if you click on the raw data table, it will actually show you the raw data that's loaded every time point that it's loaded. And if you want to use that data for something else, you can right click on it and you can click Save Table to Excel file or to CSV file. And you can actually select multiple channels here. So if I was to select, say, strontium as well, and you can click on these and save those. Normally, you wouldn't want to do that for your input data, but you might want to do that for output channels. And if you have lots and lots of channels, you can actually search for your channels up here by typing in here. So I just mentioned that we don't have any intermediate channels. These are the ones that are used in the calculation of our final results. So these might be, say, the baseline subtracted values, or it might be when we ratio each element to the internal standard, we create a new channel for that. But they're things that you generally don't want to export. You just want to export, say, the final ppm values, and the ppm channels will be the output channels, depending on which DRS you're using. If you're doing uranium lead, it'll be the final corrected ratios. Just a couple of things that I didn't mention from the messages view. In here, there's different message types. So there's information messages. This is just recording information. There are error messages, so warning messages. This is where something has happened that iolite thinks you should know about, but it doesn't cause any problems beyond just, we think this might be something you should know about. There's also these error messages. So something has gone wrong and it is affecting your results or affecting your experiment. And you can turn each of these on or off. There's also this debug messages as well. So this is information that iolite's recording in the background that, like, for example, where you've stored certain things and what iolite is trying to do. And if you're having any troubles with iolite, then you can send us this information log. You can click on this save button up here, and it'll tell us a lot about what's happening and perhaps why you might be experiencing some problems. But you can turn these values on or off so that you don't see certain ones if you're trying to search for a particular message. And you can actually search up here for messages as well. So now let's talk about navigating your data. So we do that in time series, in the time series view. So in the time series view, this is the time series view over here. If we click on it, by default, there'll be nothing shown in this main plot area here. This is the main plot area. Down the bottom here, we have this navigation plot, or the nav plot. This just gives you a guide of where you are in your experiment at the moment. So for example, this is showing where we are. So this is showing our ablations, our different spot analyses, and as we move around our data, it'll show us which particular spot we're looking at. If you click on this cog button up here, this will show or hide this setup panel over here. So this is the time series setup panel. And the time series setup panel has three parts. It has the channels, the groups, and not shown by default is the selections. You can turn any of these on or off using these buttons down here. But by default, I recommend having the channels and the groups sections on. And in the channels, we've got a list of all the channels that we have. So far, we only have input channels, but if we wanted to show silicon, we could double click on it and it would, so by double clicking on it, it adds it to the main plot area. And to remove it, we click on this little remove channel from graph button down here, this little cross button. And so if we add it, and you can add as many channels as you like, and but you know, obviously if you add too many channels, it'll start to become confusing. But sometimes you actually want to have multiple channels because the different channels are telling you different things. So some might be telling you about different inclusions, some might be telling you about your ratios and so on and so forth. So you can add as many as you like. You can actually change the color down here. So you can click on this color button. You can change the line style and the weighting down here. And I'll just remove these just to make it a little bit easier to show. But you can also change the zooming over here as well. So you can zoom in and out. There's other ways to do this. I'm just showing these here. But the most important button probably for this here is this auto button. So if you do get lost in your data, this will zoom back out to the automatic full extents of your data. You can manually set the scaling of the y-axis for this channel here. And you can switch between logarithmic and linear scales here as well. Okay, so just making sure I don't forget anything. Okay, so the other important part of this plot is these buttons up here. So up here we have some zoom buttons and some grabber buttons, and there are two for the horizontal, so the x-axis, and we have two that are for the vertical axis, so the y-axis. And you can check these on or off by clicking them. So when they're on, they're red, and when they're off, they're dark gray. And these zoom buttons allow you to zoom using the mouse scroll wheel. So if I check on this one here, the horizontal one, when I scroll the mouse wheel, it zooms in and out in the horizontal extent. If I was to turn that one off and turn the vertical one on, you can see when I scroll the mouse wheel, it zooms only in the vertical extent. If I was to turn both of them on, it would zoom in both the vertical and the horizontal extent. It's the same for the grabbers. So if I was to turn the grab for the horizontal extent and I grab my data and drag it, it only moves in the horizontal extent. And the same for the vertical, it only moves in the vertical extent. But if I turn them both on, I can drag in both senses. And this is a really quick way to zoom in on particular data. So you can grab and drag, and you can zoom in on anything that you like. So you can actually zoom in and you can actually see every individual measurement made by the mass spectrometer. These are the data points that I was talking about when I was saying iolite calculates every result on a time point by time point basis. So there'll actually be a result for every one of these data points. One of the things to note with the zooming side of things, in the vertical extent, is that if I want to zoom in on this data point here, and I just have my mouse somewhere in the screen like this, and I start zooming, you can see it can go, I'm zooming in, but it's going off screen. The trick with this is that iolite is constantly trying to center the point that is underneath your mouse. So if you just keep your mouse over the data point that you want to zoom in on, it will keep that data point in the screen. So as I'm zooming in, you can see it doesn't go off screen. But if I was to zoom with my mouse somewhere else, you can see it'll go off screen. So if you just keep hovering over the data point, then it'll keep it in screen. So that's zooming in and out. When we've zoomed in now in the x-axis, you can see that down the bottom here, we have this blue rectangle, which is showing us which part of the data is currently viewable in the main plot. So this gives us our overview and gives us some sense of where we are in our experiment. This blue rectangle, you can grab it and drag it. So once you've set a good zoom level in your main plot, you can keep that zoom level by moving across like this. You can also grab the edges of this and click it and drag it, and that will expand the amount of the extent of the x-axis in the main plot. You can grab both sides, drag it, and if you double click on this blue rectangle, it will zoom out to the full x extents. And if we click this auto button back here, we'll zoom out completely. If you do zoom in on a particular bit of data and you do get lost and you don't know where you are anymore, you can also right click on it and on the main plot and say rescale, and that will zoom out the x-axis, and you can then click on the y-axis, the auto button for the y-axis. The other button up here that I haven't mentioned yet is the click and drag area button, and if you click this, turn it on, you click and drag a box, it will zoom to the box that you drag. You can see that it still shows the zoom buttons here because I can turn it off so that when I drag my box, it'll only zoom to the horizontal extents. So if I was to draw a drag box here, it keeps the same vertical extent, but expands the horizontal sense. And I can do the same thing just in the vertical sense. So if I just want to zoom in on these, it just zooms in the vertical sense. Excuse me. You can see that the grab buttons aren't shown here at this point, and that's because it doesn't make sense. You can't grab and drag your data as well as drag a box. So if you want to turn them back on, just uncheck this, and then you can go back to grabbing your data and moving it around. Okay, so feel free to give that a shot. Yes, okay, so one thing to note here is that if I was to import a couple of channels, so I've got iron and silicon shown, but if I was to click here and start zooming, let me just zoom in on the vertical sense. You can see that it only zooms the channel that is selected. So you can see the silica values aren't changing at all, but the iron one is. So it depends on which channel you have selected here. And if nothing's moving at all, or if you can't see your selections, it's because you haven't selected a channel up here. So if I was to select a channel that's not shown, then I won't see any selections. So make sure you have the channel that you're interested in selected up here. This will probably be something that you'll come across later on. So hopefully now we've covered each part of the navigating your data. Hopefully now you can zoom in on any data point that you wish. There is the reminders here in the presentation, so you can go back to these if you've missed anything. So now we'll talk about selection creation. So this is we'll talk about the basic side of things, but can be where iolite gets really powerful, because you can make all sorts of selections and be very particular with your selections so that only certain data are selected, and you can make quite intelligent choices with these. So there's three main ways to make selections. They are manually, by manually dragging an area, defining an area, or you can do them automatically, usually from the samples browser via a log file, or from using channel data using criteria. So we'll start off with manual selections. So in this example, we'll add our baseline selections manually. So let's go to the time series view. We'll show silicon, and we'll expand everything so that we're looking at the entire experiment. And we're going to add a baseline selection just to the start and to the end. Normally we'd add a lot more, because the more selections, the better your splines. But just as an example for this manually adding selections, let's add one to the start to the end. So the first thing that we would do is we have to tell iolite what group we want to add the selections to. So we'll add a group here manually. So in this groups part here, which if you can't see, make sure you click this bit down the bottom here. If you click the plus, we can add a new selection group. So we click plus, and we're going to call this baselines. You can call it anything you like, but because it is a baseline group, we do need to check this button here. So iolite doesn't care about the name anymore. In version 3, all your baselines will always in a particularly named selection group. Now you can name it anything you like. You could call this BLs or whatever. But if you check this button here, then iolite will know that it's a baseline group. Then we click add, and now we have our group here. So it has the group name. It has a little icon telling us what type of group it is. So this is the downward button means, downward icon means that this is a baseline group, and it has the spline type here. So with our channel selected here and our group selected here, we can now zoom in on this first bit of data here. So we're just going to zoom here, zoom in on this. And to manually create a selection, we hold down the control key on on Windows, and the command key on Mac, and we click and drag a box. So I'm holding down the command key, and you can see that it adds this box. And to start off with, the box is red, has a red outline with a dashed line defining it, and it has a green line running through it at the moment. And while we're adding the selection, it's in this red mode, but if I was to click somewhere else, it changes black, and it's now in what we call normal mode. We can't change the extent of the selection while it's in normal mode. We can only do that in edit mode. So to go back to edit mode, I hold down the shift key and I click on the selection. And you can see it goes back into edit mode. When it's in edit mode, you can grab the edges and you can adjust it. You can also grab the middle and move it back and forth. The way that iolite plots these selections is that the left and right edges are the edges of the time period that we've defined, but the box is centered on the mean value of the data within the selection, and the upper boundary of the box is plus 2 standard deviations and 2 standard errors, sorry, and the bottom is minus 2 standard errors. So this is updated in real time as you're adjusting the time period selected. So you can see that if I select these data here, that there's a larger error because there's fewer data points within the selection. And you can see that as I drag it out, the mean both decreases and the error becomes smaller because I've selected more data. If I was to start to select some of the ablation period as well, you can see that suddenly the mean goes up. So our midpoint goes up, and our error goes up much larger because we have a much larger standard deviation or standard error in this case. If I was to keep going, it would actually disappear off screen. So that's just to show you that iolite is updating in real time and giving you a feel for the mean and the 2 standard errors for the data that you've selected. And you can actually use this to show the effect of including data or not including it. But once we've finished defining our period, which should be something roughly like this, then we can click somewhere else and we're back into normal mode. So now that we've added that selection, we're going to drag the x-axis all the way to the other end. And what you can see here is that we've actually gone off screen. So I'm just going to zoom out just slightly. And we're going to add another selection here. So I'm going to hold down the Control key for Windows or the Command key on Mac and drag out another selection. And you can see that you can see the mean changing and the 2 standard errors. Well, actually, the 2 standard errors don't decrease a whole lot as we get more data points because it's the actual mean of the data is increasing. But you can see it changes as we select more data. The other thing that you probably noticed is this green line that's running through the selection. And this is our baseline spline. And if we were to zoom out again by double clicking in the nav plot, you can see this spline is, at the moment, it's defined as a linear fit between these 2 selections. And you can see that this is probably not a great spline for baseline subtraction because the baselines for silicon are going up and down quite a bit. But this does give you a feel for the most basic idea of a spline in this case. So that's adding selections manually. If you're having any troubles with not being able to see the selections, so for example, if I was to add another, or if I was to click here, add another channel, actually that's not a good demonstration. But if you are having troubles, just making sure that you click on the channel here to make sure that that the selections are shown. If you can't see, the other reason why you might not be able to see the selections is if you don't have the baseline group selected in the list. So you must make sure you select which group you're going to add the selections to first. Oh, I didn't mention that you can delete selections manually by, say, I added a selection in here manually, and later on I wanted to get rid of that. I can do that by holding down the Shift key and clicking on it so it enters edit mode, and then clicking the delete key, and that will delete it for me. Okay, so as you can imagine, dragging out selections like this for hundreds or maybe even more than 1,000 samples per session can actually be quite arduous, take you a long time. So there's ways to automate this. The most basic way to automate it is to use the laser log file. And for those who haven't come across laser log files before, it's just a log file that is created by your laser software that records every time something changes for the laser. So it will be, in particular, be recording a timestamp, and then it will tell you the X and Y position at that time, and it'll tell you whether the laser was on or off and what the spot size was. And iolite can use that information to create selections. So the way it does that is that it creates a square wave, this green wave, of when the laser is on. So when the laser switch is on, it's 1, and when the laser is off, it equals 0. And it also copies across the name that you've entered into the software. And with this square wave, we can then compare it to our mass spectrometer data. So the two are never perfectly synchronized. And this is because when the laser switches on, there's usually a delay from when the laser switches on and then the measurement is recorded in the mass spectrometer, so it takes some time for the material to reach the mass spectrometer, but also because the computer clocks are never perfectly synchronized, and so they could be forward or back relative to one another. So we have to synchronize the two. But once they are synchronized, we can use the sample labels and the X and Y data from the log file, and we can use that to create selections as well. So this is what it would look like when it's synchronized properly. So the laser switches on and our mass spectrometer value goes up, and laser switches off and our mass spectrometer value goes down. So let's try that now. Let's import the gabbro_log.csv file. So we do that in our data browser, and we go to our files browser, and we click on import log. So not the import file button, the import log button. And we will click on, we'll open the gabbro_log.csv file. And what that does is it loads this file. So it loads this window here. And what we can see here is that green channel, that green trace, the square wave from the laser log file, showing when everything's switched on and off, and also showing our mass spectrometer data. So the blue is the mass spectrometer data. By default, it will have automatically tried to synchronize the two for you, and it does that using this auto sync button down here. If this is checked, it will automatically try to align the data. If you wanted to align the data yourself, you could uncheck this here. Or sometimes it will actually be confused. Sometimes there could be a spike in your baselines or something that is confusing it. Then you can uncheck that and manually do it. So you can adjust the offset here. It does actually tell you what the offset is. Here you can adjust those. But if this auto sync is checked, it will snap back to the value it thinks is best. So in this window here, we can move about by clicking and dragging the plot. And if you scroll with the mouse wheel, it will zoom in on a particular part of the plot. So I always recommend, even though it looks about right when we've zoomed out, I always recommend zooming in on the start to check to make sure that they align nicely. So we've zoomed in here, we can see it, and then checking at the end. So zooming out again, and checking the end as well. There are times where the two will become unsynchronized, and if you do see that, it's normally a particular case, and it's a timing issue with your mass spectrometer normally. The lasers we found to be pretty well recorded in their data. If you wanted to make a manual adjustment here, you'd uncheck this auto sync button, and you can hold down the shift key, and that will move this trace. So if, for example, the auto sync button was lining up with the wrong spot, you could move it across here, and then we'll see. But if I click this auto sync button again, it'll snap back to the value that it thinks is best. And in this case, you should get an offset of about -231 seconds. So once that's synchronized, we can click done, and you can see that we have this log file that is loaded here. And if we go to our samples browser now, you can see that we still have our sample that came from our mass spectrometer file, but we also have all these samples here that came from the laser log file. So the laser log file told us what time the sample started and what time it ended. So we've got a duration from it. It also records some information about the spot size, the laser rep rate, and the speed, and so on. So now we can use this to create our selections for us automatically. So for example, we can click on any one of these selections, so any one of these samples in the list, and click create selection from sample, this button up here. So if I was to click this, it would ask us what group to put it in, and it's automatically guessed from the sample name that this should be in the NIST 612 group. But if I was to click here, it will show us all the reference materials that we have. But if this was an unknown, we don't already have a selection group for it, we can actually just type into this field here. So if it was an unknown, we could call it, my samples. You can add names manually here by typing into this. In this case, though, this is actually a NIS612, and we can adjust the start and the end of the selection from what is recorded in the laser log file. So just to illustrate that, this is how the cropping works. So if the laser says that it's switched on here and switched off here, these are the two dotted lines. There is sometimes, if you have a slow cell response, there is sometimes some wash in time and there can be some wash out time. So if I wanted my selection to start from here instead of here, I could just put in a couple of seconds in the start crop section here. So if I put in, say, 3 seconds, it would move it, or maybe say 10 seconds in this example, it would move the start time of the selection to here. And similarly, if I wanted to move the end time of the selection across this way, I would put in a positive value here. You can actually put negative values in here, so you can end your selection after the laser is switched off, or you could create a selection that starts before the laser switches on, and you can do that with negative values in here, but that's how they work. We do also now have this duration field in here. So you can actually say, I want you to take off 1 second from the start, and I want the selection to go for 50 seconds, say. If you put in a duration, iolite will ignore the end crop because it doesn't make sense to set a duration but also crop something from the end of it. So if this value is anything other than 0, then the end crop will be ignored. So in this, we can actually create groups of selections very quickly. So I've just selected one sample there, but I could go through and select all my NIS612 in the experiment like this and add them all at once. But that would, if we had hundreds of selections, that could be very slow. So we can actually use the search button up here. So if I was to start typing in NI up the top here, it will automatically filter this list so that only the NIS612s, or only samples that have capital N, capital I in the sample name will be shown here. It is case sensitive, so it does matter if it's capitals or not. But if I type in NI, it will show all of my NIS612 samples. And so if I click on one of the samples there and then select all of them by hitting Control A on Windows or Command A on Mac, it will select all of those samples for me. And then I can say create selection from samples, and we're going to put them into the NIS612 group. I am going to crop off 1 second from the start and the end, just so that we don't have those wash in, wash out effects. And I'm going to click OK. If I was selecting baselines, then I would make sure I have this baseline checked here, this baseline group check button here. If I was to get something wrong in this, say I cropped off 3 seconds and I meant to crop off only 2, I could go back and repeat this process exactly the same and just click this replace existing button. And when I click OK, it'll delete everything that is in the NIS612 group and replace them with my selections here. But I don't have anything in there yet, so I'll just click OK. And now if we go to our time series view, you can see that we now have another group here. And if we click on that, and we'll zoom out, you can see that it's added selections to us, selections for us automatically. And if we were to zoom in on any of those, actually I'll just zoom in the horizontal sense. And you can see it's taken 1 second off the start and about 1 second off the end. Well, 1 second off the end as well. So we can do that then for all of our standards and our samples. So we've done it now for NIS612. Let's do the same thing for BCR2G. So if I type in BC, it'll also show our BCR2G samples here. And if I click in the table and hit Command A or Control A, it'll select all of them and then create selections from samples. You can see that it's updated the selection group name to BCR2G, and it's applying the same crop values. So everything there is fine. I can just click OK. Excuse me. And you can see now that we have our BCR2G selected in our time series plot. And if I go here and type in BH, it will select all of our BHVO samples. So now we can add those as well. And now we have BHVO selected. And we'll repeat the same thing for our our opaques. So this time, for our opaques, we will select all of them. We'll click on this Create Selection from Sample button. But this time, we're going to type in our own sample name. Sorry, our own selection group name. So we'll just type in opaque. And so now, when we go to our time series view, you can see we have opaques here, and you can see the different icons. So we have our baselines icon showing that it's pointing down, showing that it's baselines. We have a little Champions Cup for reference materials, and we have a target for our unknowns. It's really hard to think of icons for these sorts of concepts. That was the best we came up with. But you can also see that there are no splines for our samples. That's because it doesn't make sense to spline your unknowns. But we have splines for each of these. And we also have our spline types over here. So we'll complete the process for plagioclase as well. So we'll select everything here and create selections from sample. And this time we'll call it plagioclase. And we'll do it for CPX as well. Pyroxene samples. And we'll also do it for our olivine. Just remembering that it is case sensitive. We'll call that one olivine. It doesn't matter what you call these groups. It's just so that you can remember later on what they were. We could have put all of our unknowns into a single selection group and just called it unknowns or minerals. That's what I meant about, and we could still do that. We could still create a new selection group that has, let's put olivines and CPXs in the same group. So we will select our olivines. Oh yeah, we've already got olivines. So let's create a new one. So olivines. We're going to create a new selection from sample, and we're going to call this OL and CPX. And so we're going to add these olivines to it. Click OK. Then we're going to click our CPX. So select our CPX. Select all of those. And this time we're going to find our OL plus CPX. So OL and CPX group here. Select that. And we're going to add it. Now we'll make sure we don't have this replace existing, because otherwise it'll just get rid of the olivine selections we made before. And we'll click OK. So you can see now that we have our clinopyroxenes and we have our olivines, but we have this selection group here that has both of them included. This is just to show you that you can have selections in multiple groups. And then we have olivines, we have our opaques, and we have our plagioclases. So you can see that for our opaques, which shouldn't have much in the way of silicon in them, then these might be some drill throughs, or I might have just put the spot in the wrong spot. Same thing with the CPX. No, CPX looks all right. This olivine over here seems to have perhaps CPX levels, so maybe it was actually a clinopyroxene instead of an olivine, or it was a drill through or something. And the plagioclases, no, maybe look all right. This one looks like maybe it has a drill through, this second one here. So just with a couple of clicks, you can actually create automatic selections very quickly. So you can do that with hundreds of selections very quickly. We have done this manually at this point, but there's actually a button here in the samples browser called this auto selections. And what it will do is, if I don't have anything selected there, if I click all and click, so I've selected everything, all samples, and click auto selections, what it does is it will use the names and the similarities of the names to automatically create groups for us. So it looks at this name here, NIS612 run 1 and NIS612 run 2, and says, I reckon they're probably in the same group and they should probably be in the NIS612 group. And then it looks at the BCRs and says they probably should be in the BCR group. And it'll go through and it'll say, look, all these opaque names look very similar. They could probably all go in the one group, and we'll call that opaque_1. And same with the plagioclases. And so it's a brilliant way. With just one click, we could have added all of those groups and just click OK. We're not going to do that in this example here. There are a couple of things to look out for in this. So if we scroll right to the very bottom of this, you can see this NIS612_run10. And because it has this 10 in it, it's guessed that this is a NIS610 one. It had to choose between 612 and 610, and it's gone with 610. But we can just double click in there and tell it that no, this is actually for the NIS612. So even though it has tried to guess for all of these, it hasn't quite got it right in this case. But you'd see that in your experiment. If you went to your time series tab, to your time series view, you'd be able to see that there's just one selection in NIS610, and it looks just like the NIS612s. It's just categorized it just slightly wrong. The way that we do this is, the way that iolite guesses which samples are similar is this match cutoff down here. So if I was to set this to be 1, it means that the names have to match exactly to be able to be grouped together. So this CPX1 only has a group. It would form a group of 1 because there's only one CPX_1 sample, and same with all the others. If I was to set this to 0, it will try and match anything and it will just get all crazy. So for example, it's matching the opaques to one of the zircon standards and all sorts of craziness. It seems that about 0.5 is about the right value. Oops. Oh, I shouldn't push enter. I think I've just destroyed all my selections. So about 0.5 is about right. The trim, the start and end trim is exactly the same as for the others. And it has this baselines option here. If you check it or uncheck it, if you have it checked, it will, in this case, it will move back from the start of every sample 10 seconds, and it will create a baseline selection for 8 seconds that goes for 8 seconds. So in this way, we can add all of our selections, all of our samples and our baselines with just a couple of clicks. We're not going to do that in this case because in this version, it doesn't actually copy across the sample names properly. So we won't do that just now, but in the new version that's going to come out probably next week, that problem is fixed, and you can use this tool to make your selections very, very quickly. Okay, so at this point, we should have our NIS612, our BHVOs, BCR2s, BHVOs, our opaques, olivines, plagioclases, and CPX selected. And we would check all those in our time series view. Let's have a quick look. I may have deleted all my selections, but let's have a look. Yeah, I did, but anyway, okay. So this is now where we can show the selections button down here. So if we click on this button here, it will show the selections part. And this will show each of the selections that you've made in the list. And if you click on those, it'll go straight to that selection. And so you can actually use the arrow keys to move up and down through these so that you can go through your selections very quickly. If you're looking for spikes or if you're looking for drill through, then this is a really good way to examine your selections. So that's the selections, looking at selections in time view. And now, if we go back to the data view and in the selections tab, now you can see we've got a bunch of selections in here. I have all these other selections because I accidentally pushed enter before, but you can see that on each of these, you'll have some information about the group. If you click on the group, if you expand the group, you can click on the name of the selection. So, and it will actually tell you some information about the selection. So the start time, the end time, also some properties of this selection. So it's kept the spot height, the spot width, the rep rate with the selection. Mine looks different to yours because of clicking that thing that I shouldn't have clicked before. You can actually add properties to a selection by clicking this button here, and you can call it my property, or you can change the value here. But generally, you don't want to do that unless you're doing more advanced functions. You can type in comments here for about a particular section. So this selection was made for this reason, etc. And that'll help you keep track of any particular selections that you might be worried about, etc.
Can you hear me?
Yes. Is it Maria?
Yes, Luz. Well, I've been following you, but I was late. I'm using a Mac, and I was never able to import the log file. It keeps sending me an error. I'm going to tell you. Yeah, well, I'll follow you after I try to import and I couldn't.
Okay.
Let me see what it says. Okay, for some reason I closed the iolite. Oh no, here it is. I'm trying to get to the message. Well, it says cannot read date format in the laser log file. No data loaded.
Okay, that sounds like the log file is corrupted when you've downloaded it. Yeah, you can just download it again and it should work. Did you open it by any chance in Excel? Because Excel will corrupt the data, the timestamp format. And yeah, it'll do that without telling you. So if you open, this is just general for everyone. If you do open your data files in Excel, it may automatically change the date formats without telling you, which is pretty shocking.
Okay, so I should not open, just save it as without opening it in Excel.
Yeah, exactly. Or if you do want to look at it, you can open it in other, like as in like Notepad or TextPad, I think it's called as well, and they won't automatically change the values for you.
Okay, I will do that then. Thank you.
That's a good question. Yeah.
Hi, can you hear me?
Yeah.
Thanks, Bence, for the illustration. I just want to ask something about the primary channel that mentioned before.
Yes.
So you mentioned about the channel that is currently selected will be primary, right?
Yes.
So if I want to zoom in or out, the select one will be changed. I just wondering, is it possible that I want to zoom in or out 2 or more channels at the same time? Is it possible?
Yes, if you have them selected, both selected, so you can select multiples.
Oh yeah, I tried like to select 2 channels, but if I want to zoom in out, or still only one can be changed. I just.
Right. Okay. Let me just try that. Yeah, it should zoom both.
For example, vertically. Oh yeah.
Oh yes, yeah. Vertical, it doesn't do that. No, you're right. No, yeah, I guess that's not currently possible. Joe, did you have any tips for that? Sorry.
Sorry, hello?
Joe. Hey, Joe, how you going?
Yeah, good. No, I don't really have any tips. I mean, we can add that.
Yeah, I guess it'll be, we'll have to, yeah, we'll look into adding that. There might be other implications for that as well.
Thank you very much.
So we discussed creating selections manually, and we discussed creating selections using the laser log file, but let's now look at creating selections using channel data. So this is a really powerful way to create selections. So it's based on criteria. So you can set up criteria, and only the intervals that match those criteria will be considered for making selections. The good things about this is that it removes any user bias, because user bias can play a big part in your selections. But it can also help with avoiding spikes and inclusions, those sorts of things, automatically, without you having to go through every single selection and looking for spikes. And even though we're going to show an example that uses an input channel, it can also be run on intermediate and output channels. So for example, if you were doing, say, uranium lead, you could create selections based on a certain calculated age. So you could put, say, all your old zircons in an old group and young in a young group, or whatever you want to do. So it doesn't have to be done from input channels. The good thing about doing it from output channels, in the case of, say, trace elements, is that by the time you've got to the output, channels, that the sensitivity drift and the baselines have all been corrected for. So that makes a big difference. You don't have to put in as large ranges to account for sensitivity drift. So let's do an example. Let's select all of our baselines based on some criteria. So actually, just before that, I'm going to get rid of some of those selections I made by accident before. Actually, I'm actually just going to quickly redo this. Okay, so I should have now roughly what everybody else has. If anyone does get mixed up and wants to just jump ahead to where we are now, you can open a session, the session file that was included in the example data. And that is just has the mass spec data loaded, the log file loaded, and the selections have been made. Okay, so let's go to the automatic selections. So to get there, we'll go click on the Tools menu at the top here, and we'll click on Automatic Selections and From Channels. So when you click on that, it will open this window here. So this window has a few main parts. It has up here the criteria part, it has the matches section over here, and it has the time series down here, and the selections grouping down here. So to see how each of these work, let's create some criteria. So we want to automatically select our baselines. So to do that, we click on this Add Criteria button. So if we do that, and it'll automatically add the criteria to our table here. And in iolite version 3, when you're doing this, you are always limited to 3 criteria. In this version, you can have as many criteria as you like. So we have a channel that the criterion is based on, and we have a comparator and the value. So you can double click here to select what channel you want to work on. And in this case, we do actually want to work on total beam, because what we want to do is we want to select any time the total beam is less than a certain amount. So just to illustrate that down here in the time series, the quick time series view, if we were to look at, say, silicon, and if we would try and base our baselines on this channel, the problem was it would probably select our opaque measurements down here because they're down in the baselines. They basically have no silicon in them. If we wanted to try and do it via, say, titanium, you can see that we have plenty of that in our opaques, but we don't have much in our other phases, such as our olivines and such, and this 612s as well. But if we use total beam, which is the sum of all channels, you can see that we get at least something for all our ablations, our different ablations. So that's why total beam is there. It's really quite handy to be able to sum up all the other channels to get some value. So we're going to say anytime total beam is less than a certain amount. And if we use this plot down here and we zoom in, we can see that total beam never actually gets to 0. We always have some backgrounds there that's going to affect it. In fact, it pretty much never gets below about 500,000 counts. But it looks like if we were to select a value around about the 1 million mark, that we would get all these values through here. So let's say total beam is, anytime total beam is less than 1 million. And we can type in 1 and 6 zeros, or we can type in 1 e to the 6. And you can see now that the colors in our time series plot down here have changed. So what we can see is the data, so the plot is gray for any any data that don't meet our criteria, and it's blue for any durations that do meet our criteria. And now you can see over here on the right-hand side that we now have a list of matches. Excuse me. So these are anytime the data has matches this criteria that we've set. In this case, we only have one criterion. It'll be added to this list. And just like in the crop section, you can see if we were to zoom in this area here, you can see that sometimes it's including some of the wash in and wash out times. So we can increase the crop as well. And that will actually, that's not doing enough of it. Let's click it up to 3 seconds. This to 3 seconds. And that's not adjusting it very quickly either. Oh, sorry, that doesn't change the matching criteria. That changes the period that would be selected. So we can crop in and out from these start times using these crops. And over here, just because a duration matches the criteria, it doesn't mean that we necessarily have to add it. So if we were to zoom out again, you can see that if in this graph down the bottom here, if a duration matches the criteria and we've selected it, it turns green. And we can select all of them by using this select all button up top here. In this case, we do want to select all of them. So you can see that now they've all turned green, and you can see the blue parts are those cropped out areas that I've put in where it matches the criteria, but we don't want to include it. So now that we've created, we've matched all these durations, we want to put them into a selection group. So we'll select our baselines group. Because this is baselines, we will just click on this baseline group. It should be fine not to do that. We could put in a base label for everything here. In this case, because they're baselines, we don't need to worry about that. And then we can click add selections. Oh, sorry, we want to replace our existing ones because we had one at the start here and one at the end. We want to replace those. So we're going to click add selections. And now if we were to go to our time series view, we would see that we have all those there. But just before we do, I just wanted to mention this minimum duration thing here. So sometimes we can have spikes or dips in our signal that might match our criteria, but we don't want to include them in our list. And we can actually set a minimum duration here to avoid those spikes. So anything that matches our criteria but is less than 10 seconds after we've applied the crop won't appear in the list here. So that avoids spikes being included. So now that we've done that, we can close this and we can go to our time series view. And now when we click on our baselines, you can see that we have lots of selections added. And you can also see that it's doing a much better job of fitting a spline to our baselines. So you can see now that spline goes through all the variations in our baseline. Just making sure I haven't missed anything. So that brings us to splines. So we'll just have a quick talk about splines. So as I mentioned, splines can be anything from simple mean of all your selections right through to this more complex cubic splining that you can see here. And you can change the spline type by double-clicking on the spline name here in this groups section here. And if you open that pop-up menu, you'll see that there's a whole variety of options. So if we would click on this mean, it would just take the mean value of all our selections, and that would be our baseline. Not very useful for our baselines, but it can be useful for other parameters. One of the ones that are really handy for baselines is the step functions. So this step forward spline type is one that I use quite regularly. And you can see that what it does is when it reaches a selection, the midpoint of a selection, it then sets the spline to be the mean value of that selection until it gets to the midpoint of another selection. And this can be really handy if you have different baselines associated with different samples, or if you don't want to have, if you have splines, you can see that, for example, this one here, this sample here, actually has a decreasing baseline during the ablation. And if you don't think that's what's actually happening, then you have the power to change that. The whole thing with splines is that it depends on your understanding of what's happening in the mass spectrometer while you're measuring things. So sometimes you don't want a wildly varying spline. I'm trying to show an example of this. Because the spline might be showing more variation than what you think is actually happening. So you can choose the level of smoothing, or you can choose the spline type here. By default, it does use this auto smooth option. If you only have one selection, you can't create a cubic spline like this because you only have one selection. So it will just use the mean if you have one selection. If you have two selections, it will do a linear fit for those two selections. If you have three selections or more, then you can start having cubic splines with different amounts of smoothing. So that's how that works. And with the auto smooth, it tries to find a level of smoothing for your spline that has the least amount of difference between the mean values of each selection and the spline, with the maximum amount of smoothing. So that's how splines work in a nutshell, and hopefully that makes sense. And so now we've made our selections. So we've imported our data, selected baselines, reference materials, samples, and now we'll actually go through and calculate our results. So we're going to be talking about data reduction schemes, because data reduction schemes are how we go from our input data to our final results. And we'll be looking at a trace elements as an example, but it's very similar for anything you want to do. And for those people who are doing imaging, you'd still do this part because you want to calculate your trace element results, but instead of just exporting some stats for each selection, you'd actually create an image at the end. So looking at trace element calculations, there's a bunch of options in iolite that you can do. So the most basic one is just a baseline subtraction. That will give you the idea of where trace elements are high and where they're low. They won't actually be normalized, they won't be corrected for sensitivity drift, but they will give you a feel for where certain elements are high and where they're low. The next step up is semi-quantitative, and then going a step forward, we use the internal standards, and that will give you an extra level of accuracy. So the semi-quantitative approach just compares how a sample responds compared to a reference material. So for example, if we measured our NIST 612 and it gave us 100 counts per second for strontium, and we know that NIST 612 has 40 ppm strontium, if we then look at our sample and it gives us half the number of counts, then we would say it has half the concentration. So 50 counts per second must mean that it has 20 ppm strontium. And for most imaging applications, this is probably quite sufficient. This is what most people would use, I would say. And that's because in imaging applications, you aren't digging a pit, so you're not getting the downhole decreasing signal that you get for when you drill a pit. And the other part is that you might have various phases that you're going across, whether they be different parts of your sample or different minerals or different parts of the tissue, where you might not have a constant internal standard value. I think I've mentioned that bit. When you are doing pit analyses, spot analyses, then you probably want to use the internal standard approach. And the idea of the internal standard is that you will have a sample. Actually, I can sketch this out. So excuse my drawing here, but just to try and sketch this out. So if you had an ablation, a pit analysis, a spot analysis, it looks something like this, as we saw from our data before. So you have the laser switch on, the signal will decrease, and then the laser switches off, and you go back to baselines. But the problem with this is that it matters if you select this bit of data and choose the number of counts there versus the number of counts here. Because if you were just to do the straight comparison with your reference material, then you would have a different number of counts from the start to the end. But if we take an internal standard value, and we look at its response, so it will probably be doing something similar. It might have a different number of counts, but it'll be doing something similar. And if we look at the ratio between those two, they'll be the same for the start or the end. It doesn't matter. The ratio will be constant. So that's why we use the internal standard when you're doing spot analyses. So excuse my drawing there. So we do get some questions about which element to use an internal standard value. We probably don't have much time to go over all of this, but basically you want to pick something that's unchanging, usually something that's stoichiometric, and you want something that has sufficient abundance, and you prefer things that have that are free of interferences. And if you have something that's similar abundance in samples and reference materials, that's a bonus. One thing that the internal standard approach can do is it can act as a normalization factor. So if you're worried about different ablation rates, or if you have different spot sizes, which generally you would avoid, but this can act as the internal standard can act as a normalization value to correct for those effects. So this is the formula that iolite uses to calculate the trace element concentrations. This is from Longreach et al. From 1996. And basically it's just looking at the response of a sample versus the reference material and taking into account the concentration of the element of interest versus the internal standard, and it needs this internal standard concentration from for the unknown to do that. So if we look at strontium as an example, if we're trying to work out strontium in our sample and we're using calcium as our internal standard, then it would look at the strontium to calcium channel, and it would compare that to the strontium to calcium spline for our reference material. It'd take the strontium and calcium values from our reference material file, and we would need to input for each sample a value for the internal standard. Now, sometimes for, say, speleothems, this might be always the same value. So for speleothems, quite often we use 40.04 weight % calcium. For zircons, you might use 15.9 silica. And for certain minerals, you can just use a stoichiometric value for all of them. But for others, you might have to use microprobe values. And that's what we'll be doing in this example, where we have a different value for each spot, because we've gone and measured those spots beforehand on the microprobe. So one thing about this all data are processed time point by time point basis idea is that there is this calculated result for every time point in the experiment. So actually I'll skip that. But if there's no internal standard value, we can't use that equation to calculate the final ppm values. So where there's no internal standard value, there will be no ppm value if you're using the internal standard approach here. The idea with this is it's better to select as much of your sample as you can to start off with. So and then bring in your internal standard values, and then later on, then trim down your selections. So I hope that makes sense. If it doesn't, let me know in the question and answer section, and I'll go back over that. So we're going to use the example data. We should have all selected all these at this point. And now we're going to look at the DRS view. So the DRS view looks like this to start off with. So you'll have a bunch of the DRSs that come with it by default. Here's another one that I have that's written in Python. And we do have some other Python examples out there that you can download, and you can use just like the other DRSs. But the ones that are built in, they look like this. When you click on the trace elements DRS, it brings up the settings panel for this DRS. For trace elements, it's broken up into about 3 different parts. There's the external standards part over here, which has a table for each of the channels and which reference material you want to use for each channel. Then on the right-hand side, it has the internal standard side of things. So if you don't want to use internal standards, you can uncheck this button up here. This is how you'd use it in the semi-quantitative mode. So if you uncheck that button, you can see it's running in semi-quant mode, and you don't have to specify internal standards. If you do check that, then down here, this table becomes active, and it has for every selection, it has its group name, and it has the selection's name. And we can then put in values. So if we, for example, were doing speleothems, which we're not in this case, but just as an example, I could click in here, select everything, and say, let's use calcium, and we're going to use a value of 40.04 weight %. And you can see now that it's set everything to 40.04 weight %. And I could click crunch data now, and it would calculate concentration values. But this is not speleothem, so we're not going to do that. What we're going to do instead is we're going to bring in a table of values where we've measured the values in by microprobe. So what that looks like is this. You can see that we have the sample name in one column, and then in the next column we have the calcium values, and we have the titanium values. We could have, all the other elements that we measured along here, but just for simplicity's sake, I've just included these two. This is just a tab delimited text file. It's in your examples, so it looks like this. Oops, wrong button. So it just looks like this. And you can create one of those if you don't already have one by copying from this table. So you could just copy these out. So I've just selected them. I'm going to hit Control-C on Windows, Command-C on Mac, and I could then just paste those into Excel. And then I could actually take my probe values, line them up, and then paste those in. So, you know, I could then copy these and paste them in here. But they're not correct values. I'm just demonstrating here. So I'm actually going to select those out. And what we're going to do is we're going to load this table in all at once. So we can load in as many elements as we like, but we're only going to use calcium and titanium. So to do that, we click on this Import IS Values button here. So click on that, and we'll click on our Gabbro_IS_values table, and we'll click Open. Now, normally when that happens, you can't see anything changed here. But if we were to go to our selections browser in the data view, selections, and then if we were to go to any of our selections, you can see that now they have these new properties added. It has a calcium value added to it, and it has a titanium value added to it. And the reason why it adds these is that you can then swap between the elements that you've used, and it stores the values, so you don't have to keep reloading those values in. So now what we're going to do is we're going to go back to the DRS tab, and we're going to say, select all of them, and we're going to use calcium. So we'll actually pull the calcium value that we loaded in. And you can see that it's automatically taken the values from the reference materials for the reference materials. And so now it's loaded all those internal standard values for us. And at this point, we can now click Crunch, and it would actually calculate our data for us. Oh, sorry, we forgot to set the external standards. So over here, we can set which reference material we want to use for which channel. Generally, we would normally use the same reference material for all channels. It'd only be in the case of, say, something like titanium, where we have basically none in NIST 612, and so we might use, say, one of our BCRs to measure titanium. But in this case, let's just use NIST 612 for everything. So I've selected everything in this list by clicking on it and then clicking Control-A. Then I'm going to click the Set Ref Map button up top here, and I'm going to use NIST 612 here, because that's what we measured. Okay, now if we click Crunch Data, it will show a little button down here, little process thing. Our progress indicator, and it's going through and it's calculating all our values for us. So you can see that iolite 4 is much faster. This exact same experiment on this computer normally takes about 60 seconds to calculate. It takes about 6 seconds on here, so it's about 10 times faster. So now we actually have ppm values. If we were to go to our channels list, you can see that we now have a bunch of intermediate channels, and we now have a bunch of output channels. And one of the things that iolite does is, as I mentioned, it creates a channel for each step of the process. So these _CPS channels are just the baseline subtracted channels. So this means that you can actually step through. If I was to just show strontium, excuse me a sec. So if you just to look at strontium, you can see that we have the strontium-88 input channel. We have the strontium-88 _CPS channel. That's the baseline subtracted channel. So if we were to show this channel and this channel, you'd be able to see the effect of the baseline subtraction. Then we have the strontium-88 to calcium channel. This is where we normalize to the internal standard, which in this case was calcium. So we could have a look at the effect of that. And then we have the output channel, the ppm channel. So you can actually check what iolite is doing at every stage during the DRS by looking at these different channels. So now we actually have our ppm channels, and we basically calculated results. Just to go back to the DRS, there was a few settings down here that I didn't mention. We can calculate different detection limits. So the long reach et al., which is the most basic one, the one that everything else is based on. The only issue with this one is that if you have no variation in your backgrounds, so say you have all zeros, then you'll get a 0 limit of detection. The Howell et al. Approach just replaced zeros with root 7, but the Thomas Petke et al. Paper from 2012 took it a step further, and they used Poisson distribution, Poisson statistics to work out the limits of detection. So that's probably the most advanced one. But to do that, you do need limits of detection. So you do need your dwell times. So if you go to your channels and look at your input channels, at this one here, we don't have any dwell times because this was imported from a basic Agilent file. But Joe has already added a new tool that will be available in the next release in the tools menu that has a way to set your dwell times in here. So that'll be in the next release. The other thing is in iolite 3, the index channel is also the internal standard channel. Now the two concepts are separated. So you only need to worry about the index channel if you have files with different masses measured in them. So if, for example, you had one file that had strontium in it and then another file that didn't, and then vice versa, you do need to set the index channel to be a channel that is in all of your files. But in general, you don't need to worry about that. And also by default, you know, like for masking is off. So sometimes if you're working with ratios, it's very hard to see the detail in your data if you are looking at the baselines and your samples, because the ratios of the baselines will be plus or minus infinity. Whereas if you apply a mask, it will hide all of your baseline data ratios. Anyway, so that's how you calculate trace elements in iolite 4. So like I said, it could be as simple as doing it semi-quantitative by unchecking this internal standard button and then just hitting the crunch data. Or if you want to use internal standards, you just check this check button up here and you can input the internal standard values. Just make sure I haven't missed anything. One of the key parts of this though is that each of your selections, if you want to use a different value for each selection has to have a name, has to have a label associated with it. And you can type those in manually, but generally they would come from your laser log file. You can, otherwise it doesn't know where to apply each value. So, you know, this 13.38, which CPX selection does it apply it to? Well, it needs to know the label. So you do have to have labels to be able to do that. So you can copy stuff out from Excel and copy it back in again, and you can load a tab delimited file with selection labels and internal standard values in that table. Okay, we've done all that. Just a reminder that you can't get a ppm value for the internal standard channel because it's circular reasoning, because you're already inputting the concentration into that long reach et al. Equation. So the iolite already knows the answer, so you can't actually, it won't actually report a ppm value for the internal standard channel. There's a little bit more information there about the index channel if you want to look into that. But basically, now that we've calculated our results, we can actually start visualizing our results. So up to this point, we've looked at everything in time series view. So if we were to plot strontium ppm, we're looking at it in time series view. And that point I made before about there are no ppm values where there's no internal standard value, if you're using internal standards, you can see that there's no ppm values here. And that's because we didn't define an internal standard for this time period. So yeah, now this is looking at everything in time series view, but sometimes you actually want to look at what was the mean value for each of my selections. You can do that in this view by going to the tools and going to the hover stats. And up here, you can select which channel you want to look at. So if we're looking at strontium, and if you were to double click on a particular selection, it'll zoom the main plot to that selection, and it'll give you the mean value and the 2 standard error. It'll also tell you how many points are within that time interval and how many are valid values, and give you an idea of the duration as well. I've just changed that selection by accident in the background. So that's the hover stats window, but we can also get a similar approach in the results view down here. So if we click on results, you can see that there's 3 different tabs in results. There's the summary stats, the XY plot, and the data table. In the summary stats, it does exactly what it says. It will give you a summary of each selection. So for example, if I was to click on BCR2G, it would plot up the results for a particular channel in that. So we can select the channel over here. So we click on channel, let's look at strontium. That's my favorite one. And you can see here, it's showing the selection and the 2 standard errors for each of our selections. So the mean and the 2 standard errors. And if you hover over any of those, it'll tell you the values of those, the mean value and the uncertainty. You can also double click on these points and it will take you to that channel, and you can actually, so if we had a spike, we could actually adjust for it here and remove or not select the spike here. You can also, while we're on that, if we want to do something more complicated than just looking at the strontium ppm channels, we can click on this go to button and it will take us to the time series window and it will zoom in on that selection. One thing I didn't mention before was the auto button down here. The auto button will zoom to the vertical, the maximum and minimum values for the entire channel. And if, sorry, let me do a better explanation of this. So we'll look at silicon. Let's move this. Okay, so if I click on auto, it will zoom to the max and min for the entire channel. But if I was to zoom in, say, on the opaque regions here, so I'm just looking at the opaques, and I wanted to show the max and min of the data that are currently visible. I click on the visible button here. So this can be really handy if you're in an area where there is much lower counts, or if it's affected by spikes. So that's what the visible button does there. So auto zooms to the entire data set, and visible zooms to the data that's currently visible. So anyway, going back to the results view, let's just ignore this. It says you've changed some of your selections. Do you want to rerun the DRS? What that means is if I had changed any selections for my baselines or my standards, that actually affects your final ppm channels. So it's just reminding you that you might want to rerun your DRS. You can uncheck that if you want, but it's a good reminder that if you change your selections, it can change your final results and you should rerun your DRS. But back in here, so we can change which channels we're looking at. We can add different groups, and we can change the colors here, or we can double click on the colors here and set a color. And you can add as many of these as you like. Up the top here, it does give you the average value for the selections within a group. So this is taking these selections here and working out the mean value of them. The way that it calculates that, you can change over here. So you can give me the mean, the median, the weighted mean. the weighted mean is just taking into account the uncertainty. And you can actually get the uncertainty for that as well. So this is telling us that the mean value for strontium 88 ppm for BCR2G calculated using NIST as our reference material was 328 ppm. If we were to go to our reference materials and we go to glass, BCR2, and we look for strontium, it says 342. So we're a little low, but that makes sense because we're using NIST to calibrate a glass, sorry, a basalt. We're using NIST glass to calibrate a basalt glass. So it'll be a little bit off because the matrices are not exactly the same. Then it also gives us a little bit of a feel about our uncertainty. So this is going, I guess you can think of this from stepping up and up further into the levels of abstraction. So we start off by looking at every single individual data point. Then we start looking at the results for each individual selection. And then we start looking at the results for groups of selections up here. So it's stepping up the chain further and further up. You can actually, so for example, if you had some interesting observation about your data while you're looking here, you can actually go back to this notes panel that I showed at the start, and you could write some notes about this, like this shows that there is more strontium in BHVO than BCR. And what we could do is we could, excuse my terrible typing, is we could actually grab this image and hold down the Alt key and drag it into our notes. So now we actually have a little snapshot of what our results image look like here, and we can make notes about that. Then we can change it, for example. So if we were to chuck in olivine as well, actually let's remove olivine, sorry, remove the other two, just look at olivine, and we can then drag that in as well and make some more notes there. So this can be really handy, especially if you're a student and you've got questions for your supervisor. You can write them in here, or you can keep track of things. You can right-click in the notes part and export them. Or when you save your session, that the notes are kept with your session. So you can send your session file to someone else, and they will be able to see the notes that you've made and be able to understand the decisions that you've made making your data, or be able to answer your questions if you have any questions. And this, you can drag stuff in not just from here, but you can drag stuff in from here as well, or by holding down the Alt key. You can also drag in QA/QC plots as well that we'll see later. So the notes are really handy, really handy. Going back to the results again. So this is the summary stats tab. If we were to click on the XY plot tab, it's exactly the same, except that you can plot one channel against another. So if, for example, we were to plot, say, iron, let's actually put up a thing, and let's say magnesium. They should be roughly correlated. So now we have on the x-axis, we have the iron ppm, and we have the magnesium on the y-axis. And what you can see is for every selection is plotted with its uncertainty, but we also have this group value as well. So this gives us the mean for the group and the uncertainty for the group. And we can add other groups to this as well. We'll assign random colors so you can see different ones. So now you can see that, you know, our mean for our CPX is down here, and our mean for our olivine is up here. I mean, this is not very enlightening in this case, but for certain experiments, you might want to know about the correlations between different channels. In the data table, this is another way of viewing your data, obviously. So instead of plotting it, it's in a table view. By default, it has every selection along with its label, any comments, some metadata about the selection, and then it has, for every channel, it has a value going across here. And it starts from the raw channels, then the intermediate channels, then the output channels. But you can apply all sorts of sorting and filtering to this table. There are a few that we've come up with, like some sort of preset filters. So for example, if you just want to show output channels, you can click this and it will filter it just so that it only shows the output channels. Then if you wanted to show only your reference materials, you could click this. And so it's only showing reference materials and output channels now. So you can just get a quick look at your reference materials. But basically what this is doing is applying these filters here. So it's applying a channel filter, so only show output channels, and it's applying a group filter, only show reference materials. But we can also type in our own filters there. So for example, if I wanted to say a result filter, where I said only show me results where strontium 88 score ppm is greater than 100. There's plenty of those. So if we look at, let's just show output channels. So it's showing just where it's greater than 100 in this case. I could make that more extreme. Let's say where it's greater than 400. Okay, now it's limited to that. And so this just allows you to filter your results in a table sense. You can actually right click on this table and say save to Excel or save to CSV file. You can also sort your data here, and you can also, when you've selected a sample, you can zoom to it in the time series view as well. So that's looking at things, as I said, a step up from the looking at time series. This is now looking in the averages for selections. But this is a little tricky to actually know how good your data are. So we've included now this idea of QA/QC within iolite. And if you click on the QA/QC view over here on the left, and what you can see is that there's a bunch of QA/QC modules that iolite comes with. By default, there's a couple here for uranium lead ages, and there's 3 for trace elements. But you can write your own QA/QC modules using Python. In today's example, we're just going to look at the secondary check. So what the secondary check is that it looks at one of your secondary reference materials and compares it to the accepted values for that. So if you double click on that module name, it'll bring this up. So, and it brings up the module window here. You can have multiple modules open in this, but just for ease of viewing, we're going to click on this maximize button here. And up here is the settings button. So in the settings, you can set the settings for this particular QA/QC module. And what we're going to do is we're going to select one of our reference materials. We didn't measure all of these, obviously. We only have BCR2G and BHVO as our secondary reference materials. So let's select BCR2G. And what it will do is it will generate a report for you for how the group average for each element compares to the accepted value. So we have that in plot format up here, and we'll come back to that. But down here we have a table. So for sodium, it's saying that the mean of the selection means was 24,000 ppm. The accepted value is 23,000 or almost 24,000-ish here. And the percentage difference from that is 0.66%. It also looks at the amount of variation within your selections, and it tells you the percent relative standard deviation of those selections. And the reason for this is that for each element, it will give you a warning if it's above a certain amount. So you can see here that iron, in this case, when calibrating against NIST 612, is far too low. And because it's highlighted in red. It's saying it's far too low. And the reason why it looks at both the difference of the accepted value from the accepted value is that you could have a very large amount of variation within your group, but the mean could be about right. So we also give you a warning if the variation is too large. But what is too large and what is too low? Well, you can actually change those here in the settings. So by default, it will give you an alarm if anything is greater than 20%. And I should point out that you can set a warning value, which is just let me know that this is more than this amount away. And we also have an alarm value, which is where it'll actually record that something's gone wrong. And this is really handy if you're running a template, a processing template, where everything's done quite automatically, but you can actually have your processing template stop if we get an alarm from the QA/QC. So if one of our elements or more than one of our elements is off by a certain amount, it'll actually stop the processing template and tell you what's going on. If it's just a warning, it will say, you should check these results. Basically it's saying these channels are showing more variation than you'd normally expect. You should check them. So it's giving you some hints as to what's going on there. So same thing with the variation. By default, if it varies by more than 30%, which is really quite generous, but it'll give you a warning when more than 25%, if there's more than 25% value. But we can actually change this. So we could say, I want there to be a warning anytime it's greater than 5% different, and I want it to be an alarm when it's 10%. So you can see that down here, we now have warnings which are in yellow. They've now been flagged as being more, they're between 5% and 10%, so they're warnings, and anything that's greater than 10% is marked as red, which is still iron up here. And you can see these values in the plot up here. So this is just showing you the percentage difference for each element. The warnings are in dotted lines, and the alarms are in the solid lines in red. So that's the QA/QC. You can also run same thing for BHVO. And you'll see that iron is again off, but in this case, nickel is also quite a bit higher. But this is a really quick way of checking your results. And same thing again, you can add these to your QA, to your notes as well. So if I was to say, hold down the Alt key. Oops. Oh, actually, no, sorry. That one you can't drag into the notes, but is that right?
I assume you're talking to me.
Yeah.
You can actually, I think if you just, anything that you highlight in there, you can just copy and paste in any normal way, I think. So if you just like highlight the picture, like select over top of it all the way, yeah. And then you can control C, control V it, I think.
There we go. So you can add the QA/QC results that way. Thanks, Jenny. Just so you know, the element check just looks at a particular element for different reference materials. So if you measured a variety of reference materials with different amounts, different concentrations, this will plot up the different concentrations versus the values you got. So it can actually build up a sort of an uncertainty curve for you for the different concentrations. The Z-score does a very similar thing where it calculates a Z-score for each element and for each reference material. And as I mentioned, the Concordia age and Discordia age are for uranium-lead experiments. So that's QA/QC. And just as I've mentioned, you can write your own QA/QC modules in Python. We will be putting out tutorials on how to do this. And I think that they will be really powerful, and especially the stuff that comes from the community of stuff that people thought is a really good idea and has developed themselves always seems to be what works best. So we've looked at the results view, looking at things in the summary stats and the XY summary plot and the data table. We looked at the hover stats. One thing I didn't mention was the stacked plots tool. So that was something from iolite 3 that a lot of people asked for to report back. So if you click in tools, there's this stacked plot. And what it does is it aligns the center. So let's take one of laser log. So what it does is it aligns the start of each selection and plots the data for each selection. So this is a really good way to get a feel if there's any trend in your data for each selection. So if you look at any one selection, it might be quite noisy, but if you see a bunch of them, you might be able to start to see some downhole trends. Actually, I think there was one I saw in here. No. Yeah, okay. So this shows it a little bit. So if you're looking at any one particular selection, it might be hidden in the noise. But when you start looking at a bunch of selections, you can start to see that perhaps there is a little bit of downhole fractionation between rubidium and calcium in this case. And so we actually see that what is a standard glass and should have a flat concentration downhole, we can actually see there's some evolution from lower values up to higher values. So this is one way of looking for that. The Visual Age plugin we'll be talking about in our uranium lead specialized webinar later on. So we have summary stats, we have the data table, we talked about QA/QC, and now we should talk about data export. So at this point, you have brought your data in, calculated results, you've gone back and interrogated your data, so you've gotten rid of any drill throughs, you've looked for any spikes, you're happy with your secondary reference materials, and now you're ready to export your data. There's a variety of ways you can get your data out of iolite. The most common one is to export to a file. You can also write export scripts. So for example, we're about to release the PlasmaAge export script for exporting data in a particular format for uranium lead ages. It's the community agreed export format, but you can write your own as well. We do have this iolite online idea that we've been working on for a while, but it would be a way to store your results online in an online database for storing and sharing your results. And for each of these ways, you can set up favorites. So you can set up like basically a configuration file for how you want to export your results, so you can reuse it, and you can share those export formats as well. So let's look at saving to file. So if we click on the export view, you can see by default it shows the favorites tab by default. But if you don't have any favorites, if we click on the export to file, it shows the options for exporting to file. So you can choose if you want to export the mean plus or minus 2 standard errors or whatever for each selection, or if you want to report the data, every data point within your selection. Normally, most people want to export the stats. Time series is if you want to do sort of analysis of the downhole stuff later on. Then you can choose what format the file will be in. I recommend Excel because it's all then arranged in tabs. If you do CSV, it'll be like the results, then have all the metadata and stuff beneath it. Then in the selection groups here, you can see that we can select what selection groups we want to export. So quite often you want to export your reference materials and your samples, but you might not want to export all your samples, so you can actually edit this list. So you can actually import individual groups, so export individual groups like this. I'm going to deselect, oops, deselect these. And I'm going to actually do it for reference materials and samples. That's the most common thing that you do anyway. Then for channels, in iolite 3, you could only export output channels, but now you can actually do any combination of channels. But most often you want to do your output channels. They're output channels for a reason. But if you were, say, keeping an eye on one of your intermediate channels, like say your zirconium counts per second, your baseline subtracted counts, you can add that in as well. Then for each channel, you have some options for what you want reported for each channel. So you generally want the mean value, you probably want 2 standard errors, you can have different degrees of error propagation, you'll probably want the selection start time, number of points and outliers is always good. You can change values that are below the limits of detection. You can replace those values with something. So in this case, it would replace the values with LOD. You can actually type in minus LOD and it'll report it'll replace the value that was there with minus and the LOD value. We didn't actually calculate LODs just for time sense, but you can check them up here, which ones you want to export. They're not exclusive, mutually exclusive, so you can calculate all 3 and export all 3, see if there's any difference. You can include your QA/QC results and you can include your messages log as well. So now that we've got that all set up, if this is the way we want to do it all the time, then we could click the little star button and it would create a new favorite for us. So it would then appear in our favorites tab here. So we don't have to redo this every time. But now at this point, we can click export. And when you click export, we can go to, I'm going to pop this in our example file and we're going to, save it as myexport.xls. So click save. And then then it pops open this button here and you can click open file and it'll open that file that it just saved for us. So the file that it saved out, it has citations, so what you might want to cite for what you've just exported, but then it has this series of tabs along here. So it starts off with the metadata. So it has information about which files you loaded. Then it keeps track of what settings you used for your DRS. I clicked on all these DRSs, that's why it has these in here, but if you only use one DRS, it will just record whichever DRS you used. Then it has the reference materials values that you used. So in case you change your reference material values, you can actually check your results against your reference material values. And then the most important tab here is your data. So for every selection, it'll have its start time. And in this case, because we exported our zirconium values, that gives us our mean, it gives us our our uncertainty, and it gives us our number of data points, and it gives us how many points were rejected as outliers as well. And then it does the same thing for sodium, the mean, the uncertainty, the number of points, and the number of data points, so the number of outliers. So it does that for all of your selections. It will also have exported the QA/QC results. So it gives you, for each channel, the measured and the percentage difference and the variation. It also exports the plot for you. And it also includes the log. So this is what comes from the messages view that we saw down the bottom. And it tells us every time we've done something, what we've done, and it keeps a track of it there. So it would also include any warnings, if we had warnings there, or any errors as well there. So that's the export format. You can also export using a Python script, as I mentioned. So you can either load a file here. So for example, if I was to load the Plasmage format, so this is just a Python script, and it exports it in a particular value, then that's where I could select it here. Or if I selected the code button, then I can actually start importing, so I can start writing my own code here. So from pandas, or whatever, and you could write your own code there. And as I mentioned, iolite Online is still coming, still be coming soon. So I think that covers pretty much everything from importing your data, calculating results, viewing and visualizing your data, running quality assurance on it, and then exporting your data. So that's pretty much what we've got for this webinar. We now have some time for some questions and answers, hopefully some answers. But before we do that, I wanted to point out that there is documentation. So we have much better documentation for version 4, although we're still working on it. It's a much expanded version of iolite 3. So we're still working on getting all the documentation there, but it's at this website here called, this web address. We also have a blog called iolite Notes, and that's at this location here. And we also have, for all your support questions, we also have the forum as well. So the forum is still a little bit new, but we are asking all student license holders to use the forum so that we build up that knowledge base. And then we actually recommend, if you can't find it in the documentation, then go and check out the forum, because it could save you a whole lot of time writing an email, waiting for us to reply, only to find out that the answer's on the forum, and it takes you 2 seconds to find it as well. But if you can't find it there, then feel free to contact us at support@iolitesoftware.com. So just so that you can see, this is the new forum. It's already getting some questions and stuff there. It's only been available for about the last few weeks. And this is the iolite 4 blog. So we're putting up sort of posts where we look at things in more detail. So we'll take a topic and we'll expand on a particular topic. We have examples on how to do Python things for customizing things. So there's a whole bunch of stuff here as well. We'll make some announcements via the blog as well. So make sure you check that out, because there's lots of cool information there. As I said, we'll be running some more sessions. So this is just the introductory session. This is just about the basic fundamentals of how to run an experiment in iolite. But we will be doing some more focused ones. And for each topic, we'll be running 2. So we run one that's my morning time, and Joe's evening time, and we do another one that's reversed, so my evening and Joe's morning. So we'll be doing ones that are based on uranium lead, another one that will be done on imaging, and another one that will be done on automation and processing templates, and there'll be another one on how to write things in Python for iolite, so how to customize iolite that way. And I said there's a whole bunch of things that I haven't covered in this. So there's heaps of customization steps. So in the time series, once you get a particular setup that you like, you can actually save those settings as presets. Same thing with the QA/QC. If I made settings, I could have saved those settings and reloaded those. And there's a whole bunch of other things like that that we haven't covered, but we will be covering at some point. So if there are no other questions, we still have about 5 minutes to go. But yeah.
If you come up with some questions later, you can always post them to the forum.
Yes.